The atom. So the atom is very, very important to chemistry. Our theories behind the atom and the way we've come up with how an atom is shaped and structured helps us explain all sorts of chemical reactions. It helps us explain things we see at the macroscopic level every day. But we try to relate it down to something invisible to the human eye. Now, the concept of the atom has been around for a long, long time. The Greeks were actually the first to postulate that matter itself consists of these indivisible things, and these indivisible things were actually invisible. You couldn't see them. When you broke matter down, it would break down smaller and smaller to particles that we couldn't actually see with our eye. The Greek word atomos means invisible, and this is kind of where the word atom is derived from. Now, a more modern theory of what matter consists of and what these atoms looks like can be related to John Dalton's postulates. John Dalton postulated that all matter is composed of atoms. We need to modify this postulate a little bit because now we know that those atoms can actually be broken down into what we call subatomic particles. And we've even found smaller things that make up these subatomic particles. John Dalton also said that all atoms of an element are going to be identical, and the atoms of different elements are going to differ in mass and other properties. This still holds fairly true, other than we now know that we have isotopes of elements. With isotopes of elements, the isotopes contain different numbers of neutrons, and therefore they have different masses. He also said that atoms can combine in fixed ratios to form new and more complex compounds. He was pretty spot on with that one. That one's essentially unchanged. He also said atoms are not changed into different atoms in chemical reactions. If this is true, one thing we need to specify, though, we can have atoms of one element converted into atoms of another element in nuclear reactions. It's never going to occur in chemical reactions, but in nuclear reactions we can have that happen. All right, so let's go back to his first postulate. We talked about all matter is composed of atoms. We said now that we know atoms are divisible into subatomic particles, let's look at those subatomic particles. So we're going to have three subatomic particles you're going to have to know. We're going to have the proton, neutron, and electron. Now I know there's a lot of information on this table. The main thing we're going to focus on is the relative charge and their masses in AMU. So when we look at a proton has a mass in AMUs of right around 1. Its charge, its relative charge, is going to be a +1. A neutron is going to have a mass of 1 AMU. It's going to have a relative charge of 0. And an electron is going to have a mass of 0.00055 AMUs, and its relative charge is going to be a -1. The main significance of these is that protons and neutrons in an atom are going to have a much larger mass than an electron. So much so that most of the mass of an atom is going to be made up of the protons and neutrons. Electrons still have a mass, but relatively speaking, it's small compared to the mass of a single proton or neutron. The other thing to keep in mind, protons have a +1 charge, neutrons have a 0 charge, and electrons have a -1 charge. That's going to be very, very important. Okay, those are the main things you need to get out of this table. All right, so let's look at modern view of an atom. If I look at a sodium atom, and I have a sodium-23 atom, a sodium-23 atom is going to have 11 protons. The fact that the atom has 11 protons, that's what makes it a sodium atom. The number of protons defines what the element is. Always remember that. If I have 11 protons and I have a mass of 23, then I'm going to have 12 neutrons. Where's most of the mass coming from? It's coming from the protons and neutrons. Therefore, my mass of an atom is going to equal the number of protons plus the number of neutrons. Okay, so 11 plus 12 gives me my 23. And those protons and neutrons are going to be in the nucleus, which is the center part of the atom. Surrounding the nucleus are going to be the electrons. Now in this case, since the sodium doesn't have a charge, in order to be neutral, we're going to have equal number of electrons and protons. Remember, the protons have a +1 charge, the electrons have a -1 charge. So if I have 11 protons, I have a +11, which means I need a -11 or 11 electrons to get to an overall charge of 0. Neutrons, they're neutral, they don't have a charge. Okay, so let's look at sodium-24. Sodium-24 is an isotope of sodium. And what's the difference between these? Well, the only difference is sodium-24 has an extra neutron. So instead of 12 neutrons, it has 13 neutrons. But because it's a neutral atom, it has no charge, which means it has equal number of electrons and protons. And the fact that it's a sodium means it has to have 11 protons. Very, very important. Number of protons is going to define what element you have. So in this picture, if we have helium, if we look at a helium nucleus, inside a helium nucleus, we're going to have 2 protons. Having 2 protons means we have helium atoms. If I look at the graphite from a pencil, graphite is carbon, it's a form of carbon. Carbon is going to have 6 protons in its nucleus. And where do we get those from? Don't forget, periodic table, the number above the atomic symbol, the atomic number is what it's called, tells us how many protons an element has. Okay, so let's look at the relative sizes of things within an atom. Right now, an important conversion factor you need to know is that 1 angstrom, little a with the circle above it, is going to be equal to 1 times 10 to the negative 10th meters. So when we're dealing with really small distances, in particular when we're talking about an atom, we usually talk in terms of angstroms so that we don't need to deal with this times 10 to the negative 10th. All right, but you need to know that conversion. So when looking at a modern view of the atom, the nucleus is going to have a diameter of approximately 1 times 10 to the negative 13 centimeters. And a typical atom is going to have a diameter of approximately 1 times 10 to the negative 8 centimeters. Now those fluctuate depending upon what element we're talking about in terms of the atoms, but they're all relatively close to that. Now when you look at that though, the nucleus is 5 orders of magnitude smaller than the overall diameter of the atom. Now, think about this. Where's most of the mass of the atom located? Is it surrounding the nucleus? Is it in the nucleus? Is it the protons? Is it the electrons or is it the neutrons? Well, what things have a mass? The protons and neutrons have a mass. Where are the protons and neutrons located? They're located in the nucleus. So most of the mass of the atom is located inside that nucleus. But that nucleus is so small compared to the rest of the atom. What's in the other part of the atom and most of the space surrounding the nucleus? Well, that's where the electrons are. You probably heard this before previously. Most of an atom is empty space. In other words, most of what most matter is composed of is a lot of empty space. To give you a relative idea, or something to think about, and no, this isn't me, if you take this small ball bearing and put it in the middle of this stadium, which is a large stadium, the ball bearing would be the nucleus, and the outer part of the stadium would be the edges of the atom, to give you a relative scale of what's going on. But now picture taking all the mass of that stadium and putting it inside that ball bearing and then making everything else mostly empty space. So to give you another idea of this relative scale and the relative size of an atom, let's look at a calculation here. So if we have diameter of a US penny is 19 millimeters, diameter of a copper atom is 2.56 angstroms, how many copper atoms can we line up along that diameter? So what are we given? Copper atom is 2.56 angstroms. We're also given that diameter of a penny is 19 millimeters. What are we trying to find? We're trying to find the number of copper atoms. So let's come up with a plan. We've got to go from millimeters to meters to angstroms to number of copper atoms. Now, why didn't I just go from millimeters to angstroms? Well, anytime you're doing that unit conversion, once again, where you've got a base unit involved, convert things to the base unit. Don't skip that step. It helps you get the correct answer. All right, so what sort of relationships am I going to need? Well, I'm going to know that 1 copper atom is 2.56 angstroms. I need to know that 1 millimeter is 1 times 10 to the negative 3 meters. And I need to know that 1 angstrom is 1 times 10 to the negative 10th meters. All right, so let's set up the solution. We're starting with millimeters. We're going to go from millimeters to meters. Millimeters cancel out. We're then going to go from meters to angstroms. Meters cancel out. And then we're going to go from angstroms to copper atom. And our angstroms cancel out. And we'll be left with copper atoms for our final units. So let's put the numbers in there. And when we run that calculation and we round that number to the appropriate number of significant figures, we end up with 7.4 times 10 to the 7th copper atoms. What is that? Well, that's 74 million. So along the diameter of a penny, we can fit 74 million copper atoms. That's something you need to think about because that gives you the relative size of these atoms. Okay, they're very, very small. When we talk about the mole, we'll see how we can relate our macroscopic world to that small atomic scale when we're dealing with chemical reactions. So let's look at an atomic symbol. This is going to be important. We need to recognize these things, so I'm going to go through some details. You've got just the generic atomic symbol, right? I've got 2 different types here. I'm going to explain what each one is. That capital X is going to be the atomic symbol of the element, so we get that from the periodic table. Now, to the upper left of that, we'd write the mass number. To the lower right of that, we'd write our atomic number. Okay. In the picture, mass number is represented by A, atomic number is represented by Z. So Z is the number of protons in the nucleus, the atomic number. We get that from the periodic table. That's the number right above the atomic symbol of the element. And then the mass number would be Z, the number of protons, plus N, which is going to be number of neutrons in the nucleus. Now that takes care of X, A, and Z. What about that lowercase b and that lowercase c? Well, lowercase b there in the upper right-hand side is going to be the electrical charge. So whatever the charge is on that particular atom, we're going to write it in the upper right, if it has a charge. If it doesn't have a charge, we don't need to write 0. C then is going to be something we call aggregation. That's going to tell us how many atoms we're going to have together. All right, so let's look at some examples of this. So if I look at a carbon-12 atom, okay, the atomic symbol for carbon is C, right? My mass number would be in the upper left of the C, it's 12. My atomic number would be lower left of the C, which is 6. 6 I get from the periodic table. It's the number of protons. The 12 is the number of protons plus the number of neutrons. Well, if I have a mass of 12 and I know my atomic number is 6 because it's a carbon atom, then I can calculate how many neutrons I have. I'd have 6 because 12 minus 6 is 6. Let's look at some other examples here. So I've got titanium. That's what Ti stands for. Because it's a titanium atom, I know it's going to have 22 protons, and that's in the lower left. Now this particular titanium atom has a mass of 48, so it's in the upper left. So it has 22 protons, it would have 26 neutrons, because 48 minus 22 gives me 26. All right, let's look at this sodium here. So upper left is its atomic mass, lower left is its atomic number of protons. So it's got 11 protons, it's got 12 neutrons, and now it's got a +1 charge. That's the electrical charge in the upper right. O subscript 2, well, that's that aggregation I was talking about. So this tells me in this particular compound there's 2 oxygen atoms bonded together. Okay, that's what I mean by that aggregation. All right, and I can have this mercury symbol where I've got a mercury, it's got a 2+ charge, and there's 2 mercury atoms bonded together. Okay, so those 2 mercury atoms bonded together have an overall charge of 2+. Okay, so this gives us a little bit of an idea of how to write out atomic symbols so that we can report these out. And what this does is, because it's uniform atomic symbols, it allows us to communicate within the sciences with each other. We've all agreed to use this kind of notation. All right, the other thing we have to worry about is atomic isotopes. We've got uranium-235, we've got uranium-238. So if we have an isotope, and these are 2 isotopes of uranium, what's the difference between them? Well, they both have 92 protons. That's what makes them uranium. The number of neutrons are going to be different though, because one has a mass of 235, the other has a mass of 238. One of them has 143 neutrons, and the other one has 146 neutrons. Okay, so isotopes, same number of protons, that's what makes them the element they are, different atomic mass because it has a different number of neutrons. And even with these isotopes, those difference of neutrons can be significant. These uranium isotopes have slightly different properties. One's going to be a weapons grade type uranium, the other one's going to be still radioactive but relatively inert. You can't weaponize it.